Assalamu alaikum students. So we are in the third week after our midterm period of hydrology and water resource management, and inshallah we are going to study something new today. This is the situation till now. We have gone through a lot of things. We looked into stream flow in the previous lecture, and we looked how the stream flow is generated and how the stream flow is recorded. We looked into different kind of gauges and different kind of infrastructure that is usually used to measure the discharge. Today what we are going to do is runoff and hydrographs, so the factors that are affecting the runoff. We will try to understand estimating the value of the storm runoff and some other things. So we are basically, and I'll give you all the details that we are going to do today, but it is just to let you know about the place where we are in covering the contents of hydrology and water resource management. These, as usual, are the resources that I have used. The main book is Applied Hydrology, then Engineering Hydrology book, some other sources, online sources that I have used. You can check them and see what is in there. In any ways, you have to go through the text, you have to read the book. This is very important. I'll be uploading certain things on the LMS, so you have to go through them to understand the details of the thing that we are going to look into today. So as I said, these are the things that we are going to look into. Factors affecting the runoff, estimating the volume of storm runoff, characteristics of hydrograph and components of hydrograph. This is the things that we did a little bit in the previous week, but we'll again look into them in a little bit detail. What we are going to also look into detail is hydrograph separation, and we'll see how different methods of hydrograph separation are applied on the hydrograph. Introduction to unit hydrograph, S-curve, and the application of probability in determining maximum minimum of discharge is something that we will leave it to the next lecture. So let's start with factors affecting the runoff. You see, we looked into this diagram quite a lot. We looked at evaporation and the runoff process and precipitation. So component of hydrological cycle have been looked into in quite detail, and today we are going to look into the factors that are affecting the runoff process. So this is our runoff that is occurring from a certain area. We are expecting, or we are looking at the precipitation that is occurring, and then we also see that due to energy that is coming from the sun, there would be evapotranspiration, and then ultimately different processes would occur and runoff would generate. Now that we know that runoff is being generated, we can understand, or let's say we can at least guess what would be the factors that would be affecting the runoff. And these are the things that we are going to look into. In the previous lecture, we looked at this slide in detail, and we said that we can divide runoff into different components. There would be certain runoff that would be going on the surface of the land. There would be certain runoff that would be occurring just below the surface of the land, and then on the ground floor, in the ground floor, that would be another part of the runoff. We looked into these things in detail in the previous lecture. Now let us look at the factors that usually affect the runoff process. These are all the processes that would affect the volume of runoff: precipitation, size and shape of the catchment area, geographical characteristics, the meteorological characteristics, drainage net, and other factors. Let us look into each one of them in detail. First of all, precipitation. It's very understandable that the more precipitation there is, more runoff would be there, but then there are other things that would affect the volume of runoff. For example, let us look at the intensity. Now, intensity usually is measured in millimeters per hour or inches per hour. These are the units of intensity. Now, Just think about it, that if the intensity is too high, if per hour, or let's say per 15 minutes or per half an hour, if there is a lot of precipitation coming, a lot of water is coming from the clouds, then there would be less time for that precipitation to infiltrate into the ground. Yeah, a lot of precipitation is coming per unit time. The volume that is coming from the skies in terms of not the volume but the depth of precipitation, that is millimeters, it's quite high. So there would be less time for that precipitation to enter into the ground surface and then go to the groundwater. Obviously, if the intensity is high, the runoff would be high. Again, duration is another factor that would affect the total runoff. If the precipitation is occurring for a very long time, whether its intensity is slow or high, there would be larger runoff. And why is it like this? Because you see, if there is if precipitation is occurring for a very long time, we would understand that after some time the pores in the ground, in the surface of earth, would be filled with water. Once all the pores if are filled with water, then there is no other way for water to go. The only way that is left is then runoff. So if all the pores are filled, then the precipitation that is falling would directly then convert into the surface runoff. So if precipitation is occurring for a very long time, it would also increase the runoff. Coverage is again understandable. If it is occurring on a very wide area, then all the area would be contributing to the drainage process, and precipitation runoff or discharge runoff would be more. Another interesting thing is the direction of movement of a storm. You see, you would have observed, you would have seen that when precipitation is occurring, you can clearly see that there is a certain direction to that precipitation. It is falling in a certain direction, and because of the wind it is moving, if you're looking into it, either from your left to right or from your right to left. Now this thing also affects the total runoff, and as it is written here, if the storm moves in the direction of the flow, then the base period of the hydrograph will be less and the peak would be more pronounced. On the other hand, if the same storm is moving in the reverse direction, that is against the flow of the direction, then the base period would be comparatively larger and the peak would be smaller. Let us look into the diagram and it would be then easier to understand. Let's say this is a certain catchment, and these are the 2 points of that catchment, point A and point B. And let us assume that the storm, or let's say the cloud process, is moving from point A to point B. And this is our hydrograph. In the previous lecture, we looked into the hydrograph and we said that hydrograph is nothing but just the discharge process recorded in a time. So on x-axis you have time, on y-axis you have the total discharge. It is just like you are sitting at one particular place near the river for 2-3 hours and you are observing the water level in the river, and then you draw a graph of it. So it is just, the hydrograph is just that thing. So let us look into the storm, and we say that storm is moving from point A to point B. Now you see, when storm, or let's say the precipitation process, is occurring here and then it is moving into this direction, by the time the storm moves to this direction, anything that is falling here is directly going out of the catchment, and you are observing that thing. And because it has already rained here, after some time, or let's say very quickly, this water would also be reaching here. You see, the storm was initially here, precipitation occurred, the water is accumulated into the streams and then into rivers, and it is moving in this direction, and at the same time the cloud is also moving in this direction, and when the precipitation occurred here, it came out of the catchment in this direction, and now the clouds have moved out of that catchment, but because it has already rained here, all the water would then be reaching here fairly quickly. And that's why you see that this hydrograph, when the storm moves from A to B, is higher. The base period, this one, is a little bit shorter, and the peak is higher. Now, if we look at the reverse situation, the river direction is still this from A to B, but storm is moving in this direction. Now, just assume that, or just think about it, that when precipitation is occurring here, it would quickly get out of that catchment here. And then precipitation is falling here, after some time it is falling here, after some time it is falling here, and it will take that precipitation, or let's say that runoff that is resulting from this precipitation process, it will take some time to reach here. Initial precipitation that has fallen here has already moved, and the rest of the precipitation that has fallen in the further area of the catchment, by the time it changes into the runoff and reach here, it would take some time. And that's the reason that the hydrograph in that case would be having a longer base period. So this period is then quite longer. You can also see that time 1 is less than time 2, and also the peak is shorter, because you see this precipitation which is occurring here, it is getting out of that catchment very quickly, so it is not contributing to that precipitation which would be coming after some time from the further areas. In the initial case, because it was raining first at this point, and when this precipitation was occurring at that point, then this that discharge was already reaching here. So both of them were contributing almost at the same time, and that was the reason that that hydrograph had a higher peak. So the movement of the storm, or direction of the storm, also has an effect on the peak and the base period of a hydrograph. Another factor that would be affecting the runoff would be size and shape of a catchment area. It's just easier to imagine that if we have a very big catchment, it would be contributing more, or let's say there would be more drainage out of the bigger catchment as compared to the smaller catchment. So area, if the area is larger, there would be more discharge, as simple as that. In addition to the area, the shape also contributes to how the runoff would ultimately show on the hydrograph. If our catchment is fan shaped, or let's say it's a little bit bigger, then the base period of the resulting hydrograph will be less and peak would be higher. On the other hand, if we have an elongated catchment which is narrower and let's say longer, then our base period would be comparatively larger than the fan-shaped catchment, and the losses would be more, and then ultimately the discharge would be less. And by losses we mean that it's not loss per se, but the loss in terms that the precipitation that has fallen, it has gone to the ground, inside the ground, or let's say to the groundwater, has contributed to the groundwater. It's not lost in that sense, but it is because we say it is not contributing to the direct runoff, or that runoff which is appearing on the surface. So we usually term it as infiltration losses. But just look at the scenario. You have two catchments, A1 and A2. A1 is the fan shaped, or let's say it's a little bit oriented in this way, while the A2 catchment is elongated catchment. And as we said earlier, when we have this catchment, the theory is that the drainage would be occurring to these streams and ultimately to the river, and because we have a kind of shorter river, so it would reach to the outlet point quickly. You see, comparing with this catchment where the river is a bit longer, this is because it is extended into this direction, and the river itself is not that long, so it would reach to the outlet point fairly quickly, and we will see this kind of hydrograph where there is increase and then immediately there is decrease. On the other hand, if you have an elongated catchment, then the furthest point would be contributing to the drainage after some time. It would take some time for water from this point to reach to this point, so that's why you have again longer base time and then lesser peak. So these are the things that affect the runoff process. Another factor that would affect the runoff are the geographical characteristics. It's understandable that if, let's say, the surface is impervious, if the water that is falling from precipitation, if it is not going into the ground surface, and if the surface is impervious, then it would directly convert to the surface runoff, so we would be having higher discharge. So impervious top surface will increase the runoff. Sometimes we have on top the normal surface, but just below the surface there is impervious layer. In those kind of situation also we would be having increase in the runoff. On the other hand, if we have on the surface, if we have faults and fissures and cracks, then water would go into those spaces and it wouldn't contribute, or let's say it would contribute to the surface runoff but not that much. So in that case also the runoff would be affected. So geographical characteristics are other things that would affect the runoff. These are just a few diagrams where you can see the faults and the fissures and different kind of structures that would ultimately reduce the surface runoff. Meteorological characteristics are other things that affect the total runoff. If you have higher temperatures and you are, let's say, in a snow-fed area, there are mountains and mountain tops have snow, and if then next day if the temperature is high, then more of snow would be melting and it would be contributing to the runoff. So obviously the temperature also affects the total runoff. Similarly, the pressure, altitude and wind, they also have effect on runoff. They are not directly affecting the runoff, but these things, for example, wind, if we said that if the storm is moving from one direction to another, then it is affecting the runoff. So wind in itself doesn't directly affect the runoff, but because of the wind, precipitation is affected, and precipitation then in turn affects the runoff. So these things also indirectly affect the runoff. The detail of these things you have to go through the book and read them, but these are the things that we can now discuss. Okay, drainage net is another important thing. You see on the right hand side you see our river network, the Indus River network, the Jhelum Chenab, the Indus itself. If we have a very complicated kind of a drainage network, then the water, once resulting from the precipitation, the water would then enter into these canals and these streams, and it would take some time for that water to ultimately reach to the outlet point. So if you have a very dense network, a drainage net which is complicated, and there is a lot of streams and canals which are diverting water from, let's say, from east to west or from west to east, then these things would also ultimately affect the total runoff. Okay, so that was related to the first point, which was factors affecting the runoff. The next one is estimating the volume of storm runoff. So how much runoff is generated. This is important for engineering because ultimately we have to find out how much discharge is being created so that we can design our culverts, we can design our drainage infrastructure and other things. Usually there are other methods also, but two methods that we would be looking at this level are rational method and SCS is curve number method or CN method. These are the two methods that we would be looking into. The numericals would be either uploaded on the LMS, or we will do it in the next lecture. But keep in touch, or let's say keep visiting the LMS site, and I'll be uploading certain things there. So first of all, the rational method. It's a very old method and very simple method. Simple equation is this one, where the runoff is equal to CIA. C is the runoff coefficient. We take the value of C from the tables. I is the rainfall intensity, and as I said earlier, the unit of intensity is either millimeter per hour or inches per hour, and then the area. So these are the three things on which the runoff would depend: the runoff coefficient, intensity of rainfall, and the total area of the catchment. Now we use these two equations depending upon what kind of units are you expecting at the end. Usually if we are calculating the discharge in cubic meters per second, then we would be using this formula, 0.0028 CIA. Area would then be, if you are using 0.0028, the area would be in hectares. Otherwise, if you are using 0.28 CIA, then area would be in square kilometers. So these are the two formulas, very simple formulas. If you have intensity of rainfall, if you have the total area of the catchment, then what you only need is the C value, which would be coming from the tables that I'll be showing to you now. And then you can find out what would be the total discharge that is coming from a certain intensity of rainfall. This is that table. You have different kind of land uses here: sandy soil or heavy soil, or type of soil, sorry, not the land use but kind of soil here, and the associated runoff coefficient. So we'll take the C value from this, and then we will put it into the formula, and we'll get the runoff that is coming from certain precipitation event. Another method is SCS-CN curve method. It's also a very widely used method. This is the equation. You can read the text once you have the presentation with you. So precipitation minus the initial losses, we'll see what the losses are, or we'll convert the losses to some other thing in the coming slide, and then it would be easier to use that formula. I'm not going into the detail of the SCS-CN curve method because the details are not appropriate to be looked into at this level, but this is generally the formula that is used. S is the curve number, and the rest of the items would be looked into here. So you see, I'm not going into the derivation, but this is ultimately the formula that we would be using. Either you use Q is equal to this thing, or PE equal to this thing. PE is effective precipitation. Effective precipitation is also described as that precipitation which is ultimately contributing to the surface runoff. So this basically is your runoff. Runoff is equal to the precipitation minus 0.2 S. S is something that would be looked into here, and then divided by P plus 0.8 S. Now, how do we calculate S? Is as follows. So we have these two equations for two systems, for American units and SI units. We will be using mostly this, the second one, and S value would be coming from this equation, and we'll put it here. Now what is curve number? Curve number we will also look into the following slides, but just imagine that if curve number is high, it would mean that we have an impervious surface, or other way around, if you are looking at a certain surface and you see that it is impervious, totally impervious, then CN would be 100, otherwise it would be somewhere between 30 and 100. And what does this 30 and between 30 and 100 means is this thing which is coming into the following slides. So we'll be looking at two things. First of all, we will be looking at the groups. So what kind of group our soil is belonging to. If, for example, you have very high infiltration rates in a certain area, for example, you have sands and gravels on the surface and infiltration rate is high, then I would use group number A, and these are the typical infiltration rates. And similarly, looking or observing the kind of catchment or the kind of area for which you are calculating the runoff, you will decide about which group you belong to, A, B, C or D. So you have a certain area, for example, and based on the definition as we looked into earlier in this slide, that A belongs to the high infiltration rate, and similarly if you go downwards, then D belongs to very slow infiltration rate. So obviously a certain catchment would be having different kinds of surfaces, and all those surfaces would be considered, and for each surface runoff would be calculated. So first thing is the group, soil groups, depending upon the infiltration rate. Then we have land cover, or let's say the land use. There would be certain areas that would be used for commercial purposes, certain areas that would be used for agriculture purposes, and each area would be contributing differently to the total runoff. So then we have to decide about the land cover. So basically you have these two things, the hydrological soil group, A, B, C or D, and then the land use. For example, let's say you have wood or forest land, and infiltration is very high, so your number that you would be getting would be 45 or 25 of the average of this thing. So based on this table we will get the values, and we'll put the values ultimately. The curve number values would be coming here. For example, let's say you are getting 70 or 60 or 80, you'll put that value here. From this you will get the S, you'll put that S into this equation. Precipitation is already known, and we'll get the runoff. So these are the two methods that are appropriate to be looked at this level, the rational method and SCS curve method for calculating the discharge or runoff. Sometimes you have also to consider the antecedent moisture classes. Antecedent moisture classes are considering that whether the previous 3-4 days there was any kind of precipitation or not. You can look into it yourself from the book, and if there are any questions, please put them on the LMS and I'll answer them. But this was enough. So for example, till this point it is enough that if you can get value from this table, the curve number, you put it here into this equation, and ultimately you calculate the discharge. Time of concentration, we briefly looked into the previous lecture, and time of concentration is simply the time that the furthest point of a certain catchment takes to reach at the outlet point. So how much time does a water drop or a water volume take to reach to outlet from this furthest point? This is basically the time of concentration, and time of concentration is usually used in some other equations of discharge calculations. We have looked at the rational method and SCS curve number method. Both of these methods, they do not need the time of concentration, but then there are other methods which does need the time of concentration. So it was just to let you know that time of concentration is the time at which all parts of the watershed begin contributing to the runoff from the basin. Okay, So we looked into factors affecting the runoff and the volume of storm runoff. Next is the characteristics, components, and hydrograph separations. We'll be looking into these things at the same time because they all are related with each other. Okay, as we said in the previous lecture that a hydrograph is just time versus the discharge curve, and we said that there are different components of it. There is a rising limb or the rise portion, then there is a peak portion here, there is recession occurring afterwards when the furthest point of the catchment start contributing to the runoff, that is that thing, and then ultimately we reach to the normal situation when the river would flow, and that is called the base flow. Base flow is simply that flow which occurs in the absence of storm or in the absence of precipitation. So whether there is precipitation or no precipitation, that part always flow in the river. That is called basically the base flow. And then we need to separate the base flow from the direct runoff, because you see we are interested in the total discharge that is occurring from a certain precipitation event. The normal river flow is already known, but we need to find out that discharge which is coming from a certain precipitation event so that we can design our infrastructure, whether these are bridge piers or culverts or any other structure. One of the method of separating the hydrograph is constant discharge method, and that occurs that we identify that point from on the curve after which there is a rise in the limb. We identify that point and we say that okay, after this point there is increase in the discharge. So this point is directly connected to the base flow, or let's say to the point on the recession curve through a straight line, and this is one method of base flow separation. Anything which is below that is called the base flow, anything which is above that line is then called the discharge that is coming from the storm or direct runoff. This is one simple method. Just draw a straight line from the point where discharge is increasing and meet at the recession limb, and that would be our separation. Another method or another way of separating the base flow is again starting from that point where the flow is increasing, and instead of going straight to the recession limb, go to that point or to inflection point. Now what is the inflection point? Inflection point is that point on the recession curve where the direction of the curve is changing. So you see here you have the curve in this direction, and then the point after that is then changing its slope or changing its direction, not the direction, but it is changing its slope, and that is called usually the recession or the inflection point. Mathematically we say that that is that location where second derivative of the hydrograph passes through zero, and that is usually the point where we join to the point on the rising limb where discharge is increasing, and we separate the two kind of flows, the base flow and the peak flow or the direct runoff. Yet another method of separating the base flow is this one. It's called the concave method. The concave method is simply again starting from the point where the discharge is increasing and reach to the point directly below the peak flow. So directly below this point, and you start in the same direction as your initial curve is. So for example, let's say this is our rising limb, there are initial losses, the water is coming here, then there is increase, so we go in the same direction straight away to that point directly below the peak flow, and then we join this point to the inflection point. And then this is another method for dividing the base flow from the direct runoff. This method is okay, but there are problem in this method, because if you have multiple peaks, for example there is initial peak here and then again there is a peak here, then there are problems in calculating the point of the peak, that which one of them is the real hydrograph and which one is the actual peak of the flow. So there are certain drawbacks of using this method. Components of hydrographs, we looked into them in the previous lecture, but because in the HEC content it is again it's been written here, so we are going through it. We have gone through the rising limb, the peak flow, the recession limb, and then the base flow. So these are the components of the hydrograph. We looked at what are different methods of dividing, or let's say separating the base flow from the direct runoff. So that was it for today. Introduction to unit hydrograph concept, the S-curve, and then the probability methods in finding out the maximum or minimum of the discharge are the topics of the next lecture. Till then, wish you best of luck, stay safe, and Allah Hafiz.